We start this section talking about number theory, and specifically we're going to look at something called prime numbers, composites, and then look at some tests for divisibility. And so let's start by thinking about this question here on this task. If you were going to construct a rectangle with 10 squares, what would that look like? Here's an example of a rectangle with 6 squares, and you could think of that as the array model for multiplication, right? There's 6 squares that make up this rectangle. So if we were going to make up one that for 10 squares, here are our options thinking of an array model for multiplication. Again, you would have one rectangle, you would have 10 separate rectangles, 1 times 10, or you would have one with 5 and 2 on the sides. And then the follow-up questions, what about 11 and 12? How are those dimensions? And looking at the two options here, you see 11 here highlighted in yellow, and then you see the options for 12, 4 times 3, 6 times 2, 1 times 12. And then revisiting this question, right, how are the dimensions of the rectangles related to the number of squares? Right, and you can see that for some reason 11 only has one option, 11 times 1. And so that leads us to the conversation of what's a prime number. And then thinking about the definition which we have here, a counting number with exactly 2 different factors, itself and 1, is a prime number. And that's what happens on these examples of trying to make rectangles with those numbers of squares, that you only have with one option, that's all you have. And then these are what we're going to be called composite numbers. A counting number with more than 2 factors is a counting number. Is a composite number or composite. And so it's important that we study prime numbers in addition to having the unique characteristic of having only 2 different factors, one in itself, is that they're the building blocks of all other counting numbers. And what I mean by that is every number can be expressed as the product of prime numbers in exactly one way, right? And so that's what's unique about them and what's amazing about prime numbers. And so we'll show that example. Another important thing to consider is that 1 is neither prime nor composite, since 1 is its only factor. So it doesn't meet any of those definitions. And so the first thing that we relate this to is what we call factor trees, or expressing numbers as a product of primes, which is connected to what we call the fundamental theorem about arithmetic. Again, every number can be expressed as a product of primes, meaning that every number, every counting number, is a multiplication of prime numbers. And so you can see 84 broken down into a product of primes results in 84 being equal to 2 squared times 3 times 7. And then you can see, so that's the product of primes right there. You then all can see that 180 is 9 times 20, and then you break that down here. And so what you end up have seen here is a product of primes right here. And so then 180 would be equal to 2 squared times 3 squared times 5, and there's its product of primes. That leaves us with trying to do one more, 324. So what we know is that 9 times 36 is 324. We're going to break this down further. So this gets broken down 3 times 3. This gets broken down to many ways. You can say, let's go with 9 times 4, and then this gets broken down to 3 times 3, and then this gets broken down into 2 times 2, and then once again you have these product of primes, and we then conclude that 324 is the same as 2 squared times 3 to the power of 4. And so that's our introduction to prime numbers and prime factorizations and expressing counting numbers as a product of primes. You see another example here for 60. Notice there could be multiple ways, but you end up with the same answer regardless of which original factors you choose to start with. And so this is a good example looking at 60 of the multiple ways of doing this.